Hello and welcome to my presentation for Lab 3, Circuits. So the purpose of the lab is to predict and simulate the behavior of circuits involving batteries, resistors, and capacitors. And a quick preview of the results is that the simulated behavior is the same as the predicted behavior. These are the important physics concepts for this lab. First is Kirchhoff's rules, first of which is the loop rule, which states that any loop in a circuit, the delta V for that loop will be 0. The node rule states that the current going into any node is equal to the current going out of the node. Ohm's law gives the delta V across a resistor, and that is just simply the current times resistance. The delta V across a capacitor is simply the charge on the capacitor divided by its capacitance. We are given a simple circuit involving two batteries in series connected with two resistors in series, and we can calculate the current in the circuit as follows, and we can get that it's 0.02 amps. Simulating that circuit, we can see that our prediction was correct and that the current is indeed 0.02 amps. If we were to reverse the connection at one of the ammeters, the current reading is still the same. If we were to replace one of the ammeters with a voltmeter, we can see that the current in the circuit is 0. This is because the voltmeter has a very high resistance in order to accurately measure voltage. Here we can see the voltage measured across different parts of the circuit. We can see that across the batteries, the voltage is +3, and then across the two resistors, it's -3. And we can see that that is the sum of the delta V across each resistor. So here's a graph of the electric potential across the circuit. We can see that it drops a small-ish amount across the first resistor and then a greater amount across the second one. If we were to put an ammeter in parallel with a 100 ohm resistor, the current would just bypass the resistor because it will take the path of least resistance. That's why we can see that the current is higher in this circuit. So we can calculate the resistivity of a couple of different things in the circuit based on the data we collected. We can see that for the resistors, they're very close to the simulated value that we put in, and for the wire and ammeter, the resistivity is 0. If we set up an RC circuit with a battery, light bulb, and capacitor, we can see that the bulb will glow until the capacitor is fully charged, and when the battery is disconnected, the bulb will glow until the capacitor is fully discharged. For the 10 ohm bulb, it took 15.7 seconds to discharge, and it took 15.9 seconds to charge the capacitor. For the 20 ohm bulb, it took 28.1 seconds to discharge and 28.4 seconds to charge. We can calculate the RC of the circuit by measuring the voltage across the capacitor as it discharges. Here's the data I calculated from that. We can then, from this data, plot the natural log of the voltage divided by the initial voltage, and the slope of that will be 1 divided by RC, and it's -1 divided by RC. We can then use that calculated slope to estimate the value of RC, which is very close to the expected value, which is 6. As for the sources of error in this lab, since we are working with a simulation, we would expect there not to be any error at all. So that means that any errors that occurred were purely due to human error, such as timings and stuff like that. For the first what if question, if we did this in real life with a real ammeter, we would expect the results to be slightly smaller from the ammeter. This is because in real life, the ammeter will have a small amount of resistance, whereas the one in the simulation we did has 0 resistance. For the second what if question, we would predict that the capacitor would charge immediately. But in real life, there is some small resistances in the wires and in the batteries, so it would not charge immediately, as we would expect based on the simulation.